Same CH3, sir. CH3 with that you can do battery. Actually, battery also you can do. With this supercapacitor, we can do the stability is better in CH3, so battery application. With cyclic voltammetry, you can do supercapacitor application. Depends upon, we can go up to maximum 200 to 600 cycles only continuous. After that, we can't go. Our battery support is 10 amperes. So with CH instrument, you can go continuously 5 to 7,000 cycles also. CH only is possible, but other than like a sensing application, if we have all the channels and all, if you require anything, now the price is over. Like when we purchase it was like around 25 to 30,000, but now they are getting sorry 30 lakhs actually. Okay. I'll just tell them like what we are doing here with the PPT, then afterwards we can.
ఈ లెవెల్ వరకు క్యాచింగ్ పవర్ బాగున్నట్టు సింగిల్ లెవెల్లో ఉంటుంది అదే
Swing two batches. First one to take వస్తారా ఫస్ట్ 1 to 40 minutes మీ దగ్గర ఉంటారు మళ్ళీ కింద పైకి వస్తుందా ఇక్కడ రావాలన్నా స్టార్ట్ చేయండి స్టార్ట్ చేయండి So please, you can please. Please. This is not a presentation, so I just want to tell them like what.
That's okay. I don't want to say it.
No, sir. So all the participants can make the. Are you ready for Shall I start? Good afternoon, everyone. This is not a presentation. I just want to show you what is the procedure we following. Little like a history about the glucose sensor. So welcome to DN course actually. So you know KVS is the course coordinator and foreign experience. Avinash, start le
నెక్స్ట్
all came to know like what is a sensor. So especially we working on biosensors. Biosensor is an electrical device which can convert any biological response into electrical readable signal. So it could be any signal. So that signal, based on that signals, biosensors again divided into subsections. The main component of biosensors is detector, transducers, and output system. So detector, you can see like here biorecognition layer. They say it's like especially they use receptors, antibodies, and enzymes and all. And transducers based on the signal which we are receiving. It could be electrochemical, optical, thermal, piezoelectric, mechanical, anything based on that the transducer will be working on biosensor. Output system is application process, we know. So as we know, the biosensors have many applications. They are everywhere actually: food quality monitoring, environmental monitoring, and environmental heavy metal detection, water monitoring, everywhere. So we choose glucose sensor. So why we chose glucose sensor? This is a little give a glance. Actually, at the moment in the worldwide, 567 million people are suffering with the diabetes. In that, 1.2 million people are only children, 0 to 19 age. This value is expecting to be 638 to 783 by 2030 to 2045. Sorry, 2045. So, like monitoring of the glucose level is one of the extreme cases it becomes. Again, the diabetes, as I said, kids are getting type 1 diabetes. What is type 1 diabetes and type 2 diabetes? Type 1 diabetes is body won't produce any insulin. This can be like, it can happen mostly in childhood, starts in childhood. This can be like a hereditary disease, immunity system reactions, and the treatment for this is like insulin injections and implantations they do. And for the type 2 diabetes, this is comes on based on like age, after like 40 years they're saying, but nowadays every almost 25, 30 also people are getting. So body produces insulin, but it's not enough of it. Our age, it won't use enough of it. And mostly common in middle age, and like this can be a life change or any sometimes genetic contribute also happens. It can be managed with the drugs and like exercise, lifestyle changes. It can be managed. So again, now these days, like in the last 4 to 5 years, one more that diabetes is pregnancy. During the pregnancy, people are getting 1 in 6 are getting also diabetes. That is like a type 3 diabetes. That is also like it is more become a recognizable one. It has to have a solution. So these are the charts where we are showing what are the target levels for the. This is based on WHO. What are the blood glucose levels we can have in the type 1 and type 2? Type 1 is before meals we can have 4 to 7, and after 90 minutes of the like having the breakfast or meals, it will be 5 to 9. It can go up to 2 millimolar more, and type 2 is 4 to 7 millimolars, and this can go to 8.5. Even what if we won't monitor? We don't know actually we have a diabetic or not. What will happen is slowly we can suffer with this neuropathy issues, heart disease, blindness, skin infection, coma problems. Actually, very recent worldwide statistics is that in low and middle class countries, every 3 out of 4 are suffering with diabetes, and they don't know they have the diabetes, and they are not treating also. So monitoring of the glucose is very important. So when we said like we came to electrochemical glucose sensor, so why is electrochemical you choose? The optical and electrochemical sensors are the most studied ones, but with the only problem with the optical sensor was the optical components are very expensive and the bulky setup required, whereas electrochemical sensors, the portability is mainly possible with the electrochemical sensors. So hence we chose electrochemical sensors only. Rapid and accurate detection possible in electrochemical sensors. So the electrochemical sensor in 1962 actually first started by the Clarks. So he started first glucose generation glucose sensor. So there he tried to calculate the glucose concentration based on the H2O2 production. So there he used some enzymes. The enzymes can be like GOX those days. Glucose oxidase only they mostly used. Based on those enzymes, he tried to calculate how much H2O2 is presented. Based on that only, he calculated how much glucose is there, the concentration. The first generation, but here the drawback of the first generation is it requires high operating voltage. So just researchers are moved into second generation. Second generation is direct glucose sensing. So where we are not calculating H2O2 production, but here we are using redox mediators. Like there are some mediators they use, ruthenium families and oxonium families, they use as a mediators. So here the same what they use is these mediators help to transfer the electrons from enzyme to the material which we are going to use, there it will convert glucose into glucolactone. So there it will tell you the concentration of the glucose. So end of the day, everywhere electron transfer is glucose oxidation only happens. After oxidation of the glucose only, we can tell this much of the glucose we can detect based on that only. So, but here also that there is a high competition between these enzymes and redox mediators. They are not compatible. So there also they faced all false results. So what they moved into third generation where they used only enzymes. But here the problem with the enzymes is the results are very good, but handling of enzyme is not easy. So it is really tough task, especially environmental situation. It's particularly resistant to particular environments only. So while we are doing the experiment also, after a certain period, there is a degradation, it will start. So enzymes, they are good for certain period only. Long-term stability is not possible with the enzyme. So they move to fourth generation, which we are using as enzyme-free generation. Here we are not using any enzymes, anything. The electron transfer direct happening with our nanomaterials only. The nanomaterials can be metals, metal oxides, carbon materials, polymers. They can be any nanomaterials. So the direct glucose sensing happens. So the electron transfer happens between electrolyte and the nanomaterials. So normally we follow here in our lab says like any sensor fabrication, 3 steps are made. Synthesis of nanomaterial. So the nanomaterial is your wish, you can synthesize anyway. But the main concern is somebody synthesizing nanomaterial and color has been changed. So I can say that nanomaterial has been formed. So you can't say that because these days contamination and sometimes especially sulfurs, people using sulfurs as a precursors. So they thought that completely nanomaterial has been formed from the precursors. But if you won't conform with the XRD, so if you use the same nanomaterial after using the UV anything, while you're doing the biosensing, the electrode, it will be corrosive. So you have to do synthesis properly. After that, characterization. Characterization, there are many characterization for structural, morphological, and functional group analysis. XRD, primarily we use here, all we use XRD. Once we prepare the nanomaterials, we confirm with the XRD. After that only we move further. So these are the some materials we synthesize in our labs, our seniors actually. So these are MMO3 dots. And again, you can ask me why there are so many shapes. So actually the research can be at any level. It can be at synthesis level. You can use different precursors and different reducing agent, different methods. So everywhere the chemistry will be there. So our seniors, some of them will work on nanostructures. So how the nanostructures are affecting on sensing behavior. These are some of the nanostructures they prepared. There are some rods and like they are like a dumbbell shape and some of them are like a disc. And as like we worked only plain graphene, GO, RGO, and single wall carbon nanotubes and multi-wall carbon nanotubes. So these are the some of the these are the composites in situ, ex situ preparation. And these are like a broccoli structured for H2 sensing, Shahita membrane, and these are for the like they said like dried ice sheet like structure. So it is prepared by Harish actually. So we work mostly somehow on the structures only. Here, like this is the biological synthesis we did. Actually, the CNDR we used egg white, so that is like a good binder. So we got rice grain like structures, and there are like the others are like some of the web like structures, some are the twisted, and these are like archin structures we got. We do work on structures also here. Just stand it and. So these are the MXZs which I am working. These are the MXZ nanosheets T03 So this is synthesized in our lab. So MXZ nanosheets you can see more like they are like individual sheets. You can see more in them. And this is the setup. Actually, we are using cyclic voltammetry. So as I said, we preferred electrochemical sensors only. This is the basic cube. Actually, first you can see this is the galvanostatic and potentiostatic 302 cyclic voltammetric station which we have. This is the setup you can see. So the major parts with that is 3 electrodes are there. So it's a 3 electrode system. So working electrode, reference electrode, and counter electrode. So where the oxidation and reduction happens at the working electrode place, reference electrode is it works as a reference to measure the point of voltage actually. Counter electrode completes the circuit actually between the working electrode and reference electrode. It completes the circuit and balance the current flow. And you can't see actually. So these are the electrodes which I want to show you. Platinum is a counter electrode, that is the standard electrodes we have been using, and the reference electrode is AgAgCl. This is the glassy carbon electrodes. Previously, we used to 5 years ago, we used to use glassy carbon electrode. But as the advancement came, everything as the portability is playing a big role, so we just came to screen printed electrodes. We used FTO electrodes also. Now the carbon papers are game, and carbon cloth also is there. Some people using meshes also. So you can use working electrode, can be your choice. You can use any working electrode. So how you're coating and how the measurement is happening, that is the chemistry you need to understand how you're coating. So now we are using screen printed electrodes. There are many types.
Yeah. For every working electrode, the result is same?
No.
Or it varies?
Based on your bare one.
Okay.
How your bare is there, based on that only that result.
But you said based on your choice, you can do.
Working electrode choice is yours because, for example, screen printed electrodes, some people can't buy it. Like we got it from Metro Home. So if some people CST instrument, I don't know how compatible is this one to that instrument. So they can use glassy carbon, that is a standard one for everything you can use it. FTO they can use it. So then they can use tin doped also. So different things they can use. Carbon cloth. Only thing is the area, how much you are coating the nanomaterial is only the matter. The screen printed electrodes, we got carbon, gold, platinum, and graphene based. So we are mostly using carbon and gold based only. So this is how we are fabricating the electrode is. First, primarily we take the bare electrode, and here I am showing the PVDF binder NMP I'm using because I work primarily with the polymers. Polyaniline is not soluble in water, so we use NMP. NMP is an organic solvent, and PVDF is a binder. Why I use binder is I don't want the material to be come off in between. Also, sometimes when we do many tests, actually the test should be done mostly 60 days. I don't want any electrode to come out. So I want the electrode to be, so I'm using conductive binder only, that is PVDF binder, it is a conductive only. So we will mix based on, normally we take max is 1 mg only. So 1 mg powder we will take it, we use 20 micro to 40 microliter of NMP and we will add 1% of PVDF binder, how much powder we take. So we'll mix like a slurry or we will do sonication. From that, we will drop cast on that electrodes, and we dry at room temperatures for the polymers. Metal oxides you can dry at 60 degrees, and we leave it for 60 minutes to 4 hours. How your material easily can be dried. So after drying, we use for the experimental purpose. Again, as I said, the CV, there are 3 modes are there for operation. One is potential static, where you keep potential is constant, only current is varied, and again another one is galvanostatic, where current is constant and potential is varied. We use mostly potential static only. For the sensitivity calculation, we go for amperometry. Amperometry is potential is constant, current varies with respect to the time. So we keep the time scale 1000 seconds, 500 seconds. In that seconds, how the current is varying with respect to the concentration of the glucose. So this is the setup actually. So I will show you, we have some coated electrodes and bare electrodes. I'll show you, the main concern here is, we will do every experiment based on glucose, we will drop it and we sense the glucose, but we will tell the results in enhancement in the current only. So we can't see anything else. People think glucose sensing I can expect. No, we will expect everything in the current variation, current what we are getting only. So bare electrode, for example, if we are getting bare electrode 10 microamperes current, after nanomaterial, the current has to be increased actually because of the electron transfer capabilities and all. After adding the glucose, the current has to be more rather than bare electrode. So that is what mainly we need to check. So the mechanism here, I am explaining about polyaniline mechanism only. You may ask what is the mechanism behind of it, how it's sensing. So we do the whole experiment in an electrolyte. We use NaOH electrolyte here. So NaOH will be divided into Na plus and OH minus. This OH minus plays a major role. These works as a main convert the glucose into glucolactone. Polyethylene has two oxidation states, so I wrote polyethylene as a pani actually. So pani react with continuous flow of these NaOH, sorry, OH ions. The OH ion, what it will use is two electrons during the oxidation. So it will form pani 2 plus NaOH minus. This helps to convert glucose into glucolactone. So how you can tell, ma'am, like by seeing that graph means the enhancement in the current only, I can say that the glucose oxidation has been happened. So this is the main mechanism happens. So the metal oxides, like if you use CuO, then it reacts with OH, it will form CuOH. So these kind of conversion happens with oxidation and reduction. So this will help you to convert the glucose into glucolactone. Yeah, I can show you the experiment actually from here. And one more thing is like we never just stop. So normally we do validation because to use any blood sample we need ethical permission. After taking the ethical permission, everything, we compare our results with the what we got in the lab and what we can do with the glucometers are there. Even in the labs also you can test. We always cross check with those results. Are we are getting like a good results or the accuracy is there, because we do use serum samples here. Those serum samples are the same person, we can use the glucometers also. So we always pretty much make sure that the consistency is there, because these days of paper like only glucose sensing, seriously they will ask for real sample analysis. For that you need to have that consistency mandatory. If it's not there, somewhere some mistake is happening, that can be in the glucometer or we are doing that in are the person's blood, like what time they took it, those are the parameters you have to check it. So I will show you this is the electrode, you can say the C, that is the electrode, the I will show you actually this. These are the electrodes. Actually, these are bare electrodes. I shouldn't handle it without gloves, but it is heavy. I just took it. So these are the bare electrodes. You can see, like there are every cell is inside of this only. So there are three connections are there. You can see on the bottom. So the middle one is a working electrode where you put working electrode. The line actually over that one is a counter electrode. So AGCL you can see in silver color somewhere here. It's a very tiny line you can see. So the whole electric circuit inside of this cell only, the connections are here. So this is a connecting cable we have. This is a 3 electrode connecting cable. We connect directly to the CV. So it gives us the results actually. I just have it in there. It comes with a microphone only, 2.1.4 actually. So primarily we use that one.
Give some gap for the camera. Actually, okay. Okay, camera. కొంచెం జూమ్ అవుట్ చేయి ఆప్షన్ లేదు వదిలే అవసరం లేదు సిస్టమ్ అవసరం లేదు దే ఆర్ సీయింగ్ దట్స్ ఇట్
Advantage. So primarily we use NaOH, right? So you have to use micropipette, and every time you have to count in how much you are pouring. So now for the demo only, I'm showing droppers. So for example, I'm saying you have to drop exactly. So it's spreading, actually everything needs to be covered. The working electrode, counter electrode, and ACC here. So this you need to be handled very carefully because BCS cube is the cube actually inside. These are the electrodes. This is like a platinum electrode and AGCL also there. So this is a working electrode. As I said, this is a glassy carbon where you put your nanotube. So this is a very standard method. So if you want to test something, you can do this method. But like we did many trials. After doing many trials, after that we came to screen printed electrode. And with this, actually, you can do reversive filtering also. Electrophysical reversive filtering because there are gas inlets are there. So this cube is called BCS cube. It will come with the setup only actually. So the electrodes will be increased also. The size will be reduced. But to be honest with you, Chennai-based companies are doing with less. This is cost like 90,000. Because this is only compatible with this instrument. But Chennai, we got it all the electrodes like 18,000. There are some manufacturing companies. You can get more setup there. If you have CHG instrument or this instrument, you can just need to play with it. Like who are very good in electronics, so you can play. So once I'm done, so you will have this agro lab connections. The black one is the counter electrode, and this blue one is like reference electrode. This is AGCL. Red one is the working electrode, and the green is the ground. Actually, for everything you need a ground. So the ground we won't touch it. So we won't do any changes in the ground. So now we do these 4 connections to this cable actually. So here also you need to understand while coating also you can't randomly coat it because the quantity you are coating sometimes it will be very less. You can get only bare borders. Even the quantity sometimes you overcoat it, it will get thin. After pouring of some electrolyte, it will come up. So you need to be very optimized with while coating. If you are using microscope or anything, you can check it. And after the experiment also, for example, I am saying the area is like this whole area is 0.1 centimeter square. After you coating your material, how much the material has been coated, there is a calculation for that. Like is it 70% is coated, or like how much is working electrode area is working, that you can calculate using Randall's equation. There is the equation based on that equation, active surface area you can calculate it. So once software is open, we do cyclic voltammetry. This is potential static. So here primarily we run with 1 to -1 Windows scale rate. So where the oxidation is, here mainly the redox reactions will happen based on oxidation and reduction. It will show you the some ones. Some materials won't show it because of high conductivity. You can't see those oxidation reduction ones. So I quoted polyamide. It's a polymer only. Hopefully it will show it. So the start potential is like these are the just analytics. You can play with it also, like how the circuit you can improve it or not. So this is the upper potential. I am using +1, lower potential -1. Number of scans. Here the number of scans I'm using 2 scans. The first scan we never take it. And scan rate. So these scan rates you can start from 1 to like 500 scan rates you can use. So for biosensing applications, mostly we will start with 5 to 100 only. We won't go beyond that because we don't need it. So now I'm taking scan rate means we are giving a voltage electron transfer rate. We are just pushing it. So the scan rate is like a point volts only, point 0.1, 0.5, 5 we are giving like that. Again, the window will start from -1 to 1, but some materials you will get 0.4 to 0.8 only. So you need to first you need to run it couple of times and you need to get an idea where the oxidation reduction things are happening. So our mainly glucose sensing is depends upon the redox reaction only. So we need the oxidation reduction. So that area that space is enough. Like if you want to test any material, first you need to only major step you need to do is you need to pour the material and you have to see what is the difference of current is happening between working electrode and after adding the glucose. So that the current difference only will tell you the oxidation is happening.
Screen.
Electrolyte, I quoted. That is where electrode, carbon electrode. And that I quoted polymer nanoparticles. And after I got the electrolyte. So by the one is different one. Working electrolyte, that is the counter one. Where I quoted another one is counter. This black one is a working not where we put material. And this is the light that is counter. And the electrode you can see. That is
reflect transfer type electron.
you can take it. Central part is another way working we will go. So we quoted here some other. And top of
The
that.
tower helicopter remote.
This round like a cap with pieces counter. This is counter. Very tiny, small PVC, just
When it's so big, we can make it in okay, why? It would be it would like we just that is a nano size and micro sharp we can get easily right without no.
As I said, that's primarily every test after that we use it and we give it. But the problem here is for things with the reference we leave it actually. So because glassy carbon only we found couldn't find much difference with this with the reference. Ferricyanide without ferricyanide, so it's just a cleaning as you said. So we got nanomaterials right there. Without any particular and we go directly in India with only the spin. But to test the material actually, we primarily go by the test it, how the material is working, is it really reaching the conductivity or not? Because here people are working on biological chemical hydrothermal. So conductivity makes sense. So is it actually conductive or not? Yes. Yes. This is a screen printed electrode also, like, we, what I call it, actually, this is for like, zero electrode, like, yeah, for that conversation, we use it by fabricated device, completely that only, not, so that is also very important. So, screen printed electrodes, in electrochemical figure, we copy these, the one that we so they fabricate those devices with that sort of thing. So we follow that only, like, here two things are there, sir. So as you are material scientist, you want to say my material is the best. So we never move it first. We go with the minimum point 0.1. As for the real sample analysis, we go with first. Yeah. This one is again. So here I just want to show the operation reduction reaction. So for the human sample analysis, we go with the PBS. But here now the question is PBS. All the time PBS won't work. Even if your material works better also, PBS won't push that. So like, we think that this is not good. So at that matter, what this we are saying is, first test your material in 0. Low concentration of NaOH. NaOH helps to push the electron transfer. Then you can say, it has minimum reaction, so it will work. Then go to PBS. PBS also, first you need to check like almost 5 to 7.4. Our human check is almost 5 to 7.4. So you need to test it where your material is fixed. And again, it is like a validation. It takes a 1 month of time to get the sweat, human sweat, your application, sweat and it is a PBS only. So even we published in ACS, actually we got the reviewer like, his mind is complicated, but he was like, he wants every solution from his but my sweat is different.
काम करेगा हमारा पड़ेगा
From there we convinced him, but he was fine. But the question is related. You belong and if I use PBS, then you are, for example, my connectivity is really good. Okay. I have not transferred it like very fast and I can get rapid detection in PBS. I won't get that. Because of the material, the electron transfer is not happening. PBS is like 0. So now, when batteries also, see, even batteries also, they're using solid electrodes. So, which is not very harm because they are in packets, they are not in electrodes. You won't touch. So, and here, we're working at the moment of wearable electronics. So, we want like as a watch or patch kind of stuff. So, where we are not going to use any PBS solution. So we're going to put any, like a bag of solid electrolytes in the form of any voltage or any polymer. But as you said, PBS is mandatory. So if you go to neurotransmitters, minds and all sensing, that part is super below. Because it's absolutely the CM papers are that we don't put it in any of which only. Beyond that, it's not the cases of PBS issues when you're doing dopamine, serotonin, Parkinson, Alzheimer's diseases, when you're relating something, the experiment has to assume PBS. But remember one thing, PBS, the sensitivity never goes after 100. And in your moment, you go to up to 1,000 in the other. As you said, we need high sensitivity. Because some people think of only material. My material is good electrode, I can say. Some people say you need to do real sample analysis. In that case, it both won't work. Some cases only work. But recently, one of the reviewers from ACS was suggested again, you do all the electrochemical studies in NaOH. When it comes to real sample analysis, you make mimic samples. Mimic means artificial sweat and all. Get the mimic samples, try both of them. You do this, you do that. What is the factor you're getting, the differentiation? Then finally, you do PBS. We did it in both actually. We didn't show much difference for maximum 10 plus or minus 10. So that always we need to keep in mind is the validation is very important here. So as we said, people sensing is very important. Ethical permission. So by using the blood, you are just taking human blood. Ethical permission, so all things are matter. So here you can see actually, first scan was not very. So here I'm using -1 to 1, that's a very big scale actually. So here you need to play actually. So I can see the little oxidation comes around 0.5. So here what I'm thinking is I want to reduce the cycle here only. So maybe 0.5 to 1. So like that you need to play with that, then you need to get the oxidation reduction. optimization is going on. So you guys are working on several. That is absolutely. You have that is kind of what glucose is. Again, it depends on applications also. Where you're using it. It's like invasive. Depends on invasive, you need to be very careful. Non-invasive, it's okay, challenging. It can be. Then we asked actually pH has been 3 levels we consider and the time of synthesis we consider. And after synthesis material will have one pH and 0.1 molarity is a 13 pH. So this pH is base pH. So in acid pH also conductivity comes very high. The H2SO4 you can use it for the but it's toxic, right? You can't do it as you want to go to biosensitive. So that is the one of the standard we use always like this. So we also got many questions. Almost 7 videos we got a question. NaOH PBS. The consistency is like and finally in ACS we said what we done was one of the videos actually is edited. He himself explains first. You just do like this, then there will be consistency. So then only we got and here the two things with the cyclic complementary amplification, where you want to tell the sensitivity. Sensitivity only matters. So now I'm doing CV and amplification test. And where I use differential pulse oximetry. So differential pulse oximetry I won't use ES. ES I won't. But again now presently people are telling based on ES also sensitivity. So they are using only ES. But here I'm using differential pulse oximetry. Previously we used to throw at 1.1 so now we are using DPV or LS for square wave. So like we choose different actually. I choose DPV. My other colleague she's working on Dopamine, she used square wave. So it's depends how you explain it. But only thing is, chronoampiometry to the step calculation to DPV, I found the sensitivity. I can go to nano levels. I got 5 nanometers low level of NOD with the DPV. So very sensitive. So because it's finding the primary first and last in between the pulse. So like before and after the seconds of current is very important. It plays a major role and it can be detected less than 1 second also. That is also. But end of the day, it's all great. So even like reviews now, if you use nanometer, MX is also they say there is no nanometer. There is no space for like nothing we need to do. Everything we have to calculate. So as I'm saying, some of the calculation what in the service, those are higher calculation. Some of the calculations. So we never give it in India. So we do academic research. The MTechs are coming, PhDs are coming. We say synthesize by changing pH, changing reducing pH, and there is something we will try to publish. So, but there is not good. Every time you have to have a device. But here, PhD level, so we work on approach MTech level synthesis and characterization setup. But here, J&D role is MTechs also need to have one. So they also work on applications. Mostly sensing applications. Like our supervisor, he works on sensing, gas sensor and electrochemical sensor. And now people they just want text, they don't want to work on sensor, they want energy. So people don't work on energy. It depends upon your choice. They need to monitor the kind of what they yeah. I kept only 10 scans because if I kept 5 scans, maybe we can't say any oxidation, but we know some of them are very rare. So now you can see here the oxidation is one reduction in the and it has two oxidation. Theoretically, it has two oxidation, it has to form two. So that's why I kept it as scan, at least we can see. Titanium has like 4 oxidations, so you don't show 4. Some of them are Actually, normally, unless we keep just to run the scan rate, we keep 1 millimole of the example, if I say. I will do 5 to 100 scan rates in that one. I just say diffusion control is happening on the skin. I am increasing the concentration, sorry, scan rate, is the current is increasing or not? So first we check is that. So after that, we start normally, it's like, again, spec sensing is different, glucose sensing is different. Spec is manual, 100 micromolars will be there in your spec. Blood is, you can go to 5 micromolars. So what concentration you want to take is that, you are the master in that. The minimum is 10 points to get a calculation. So, usually calculation theoretically. Minimum 10 points are required. So that flow we take 10 different concentration. Sometimes what CEOs and people says is you can take 20, best of 10 you can take it. But that won't work. Best of 10 means straight line we can take it, right? So normally we consider 60 points, 50 to 60. We do several cycles. We do the scan rate, then we do the different concentrations of the glucose. Then we run for DB. That not have to be there in the 60 because that's why I use PVD pointers. So now I'm done today experiment. So I got some results. What I'm doing is I'm calculating sensitivity. So today is my first day. Again, in 10 days, after 10 days, I do only CV or DPVD, one only assist. So I want to see that what is the current. So now today I got 90% current. Again, after 10 days, 90% won't get it. Until unless we have like a clean rooms and all, then only we will get it. And we won't keep electrodes also like somewhere there. We just either we keep it in desiccators or just here with the petri dishes we close it. So it has to show degradation also. If someone says 90% also, people say they question that it's not correct. So we tested the 6 times in 60 days. So that based on that only the retention is there. Starting we got this from the conference. So this much of RST is there. So this electrode can be used. That RST also one of the important factors to Now to show you guys, I will start to now we use micro.
So we can't manipulate any
It's like laser.
Adjusted you see what is that? Where is the source? Adjusted you. We'll explain it. We'll explain it.
Then after explanation shall be sonic
Sample. Paper. Some cases. Put in there. Put there. Where is speaker, sir? Please don't stay there. You're coming.
There's one good side, right?
See, you got your sample. No sample there. You do some fiction, that sample.
What is our one?
You take this. Come here and do this one. You learn first. You have to prepare the sonicate. You have to sonicate the sample. Disperse the sample. Then focus. Here you can see this is a 5 sample position sample area. Okay, one is reference, one is standard one. There you have to put, so this is double beam spectrophotometer. There you will take blank reference as a reference, then measuring there. Then you have to what pass the UV visible light. Okay, so here you can see the UV and visible light is passed through reference lens and sample set, and the difference of intensity passing through sample is detected. That is detected and photo multiplied, and you will get a display across. Okay, you will get observance versus wavelength. Okay, and it works on Beer's law and Lambert's law. So Beer's law tells us absorption is proportional to number of observing molecules. That is the concentration of sample observing sample molecules. Lambert's law is nothing but fraction of radiation observed is independent of intensity of radiation. So these two laws will be useful in the UV visible spectroscopy. So you will get the observance versus wavelength. So where you will get the edge that is absorption edge. That edge will tell you the maximum number of observations taking place there. So from there you will calculate the band gap. First you have to calibrate by doing cell matching, and afterwards you have to set. First you have to activate the UV light, visible light. Then go to the scan parameters, check the speed, then view the intervals, okay, wavelength, then mode, select the mode, then okay. You can change it 200 to 1100. The instrument wavelength range is 1100 to 1100.
Here.
Sample name చెప్పండి.
Sample name.
Sample name, use sample name. So you are giving the wavelength range and is scan rate. So these are different types of what transition. Five to five. There are different types of transition. So you can see that exact depends on the orbit of okay, the atom present and nature of the bonding. Generally, pi to pi star, pi into sigma star. So different types of transitions. Okay, these transitions will helpful in the analyzing of the.
Sir, only for type of transition.
Yes.
And then we are having this absorption under some scale. So from that, we should understand which transition is what.
Yes, according to the observation side.
So
Band. That
now
absorption
this
rate.
is 528. So how we can check which one is transition happened? How we can
Generally, of match literature. Number two is whether the graph should be blue or red. Blue shift indicates decrease in size. So shifting the graph also is knowing the which type of transition.
what kind of this the different area will be there.
Yes.
So it is like this establishing the range of 200 to
There will be a specification. For 200 to 400, you have to identify which satisfaction in the which range. Your particle is giving a subset of wavelength 200, 300, 330. Falls in the which range. So match will be wavelength range.
अभी दोस्तों जीवन आज के घटने
Make it wavelength.
related can we put that transition like S2, S2 like that we kind of
You will produce so here you got the peaks there. This is due to the concentration happening here. So it is having 1.70 observation. At 372 it is having observation 1.50. So these it depends on the what the particle composition or particle size. You dilute it. Again you repeat and do the dilution. Then check.
at least we have to check 2 times.
2 times. See, this is I think concentrated. You dilute it and check.
ఇప్పుడు 200 కదా ఫాలో అవుతున్నాం 200 కదా
The solution or see, in U, characteristic means in UV you have to find out 4 points. Number 1 is observation. Okay. Number 2 is what transition. What type of transition? Number 3 band gap. And number 4 the curve, the shape of the curve, shift of the curve. What it indicates? Whether it is blue shift or red shift. Blue shift indicates decrease in particle. There only you can decide whether it decrease in particle size or increase. So you have to analyze meaning of that. Find out the absorption age, maximum absorption age. From that you understand what type of transition it is. Then afterwards go for basic calculation. There, for example, ZNO, direct band gap. So go for direct band gap plots.
Sir, in crystal it is having broad band, broad this,
Yes,
this is
sometimes you will get some broad band. Broad, it indicates what where different particle sizes. Okay, Yes, broadness indicate different particle sizes and gap.
And in particular range, that also is there. 200 to 400, 500 range.
Yes, some will get observance at 200, 400, above 400. Visible range.
Yeah,
Above
if you
visible
give
range.
this to this much light, that is also that particular property.
Particle problem, based on the particle problem.
Sir, is the area is there anything related to this particular area?
Area you can't say, but you have to make, you have to get the absorption edge. Absorption edge, maximum absorption band. For example, gold nanoparticle. Gold nanoparticle shows different colors. The different colors, why it is showing? Because of plasmonic band. You have to get the plasmonic nature, not UV. That's what plasmonic band. Silver will also shows plasma, surface plasma resonance band between 300, I think 300 to 500, 400. So you get everything. Mainly optical properties. Find out the optical properties. You see, go to graph and have to pick. You can see it is got lower shift. Small observation rate.
Sir, it is started from here, right?
Yes, from 0.79. Due to the what observation, how it is interacting with.
Some points are missing there, that they will give.
That is due to the observation you will be getting there.
And that, and area, there will be a layer of function. That's why they are doing. So it is starting from the higher to
Low. See, you have to repeat the analysis by diluting, okay, by measuring the concentration, okay, 4 times until you get. See, first you do the literature survey. For example, you are working on ZNO. You do the literature survey where ZNO is showing the absorption bands. Then do the experiment. Repeat the experiment there. You have to get match. You have to match your peaks with the reference peaks. Then only you can tell your particle existence, absorption, nature. Then go for calculation.
See, sample
Do the repetition there. First do the literature survey and find out the absorption peak. For example, in literature they will mention ZNO is observing, showing observance at 300 to 400 nanometer. Similarly, you have to try for that. And this is what plot, band gap plot. Okay, for top measurement. You take your wavelengths, observance value. Okay, according to top formula, this I made Excel sheet.
Okay.
So here you will get H nu versus alpha H nu. Okay, and here H nu it is for indirect and it is for direct. So you plot direct versus H nu and indirect versus H nu. You will get direct and indirect transitions. You can see here. You can see here. You can see in this one. See in this paper they have mentioned here. You see direct and indirect plots. You have to. So for here the plot you can see here the variation of observance of sample with incident. This is what you are getting primary graph. Next plot of what A1/2 versus E photon. You see indirect transition. Okay, this is for alpha H nu whole square versus E photon. So where the tangent touches, that gives the band gap.
Sir, can you share that?
I will
Excel
put it
sheet?
in group.
Excel
I will
sheet.
put in group. You can see. And you must understand here. You can see some of the examples I gave here. Now, example for you see. For example, you are getting like this graph. 4 points you must know. First, get the absorption peak. Second, high absorption at lower level. How absorption is varying with the lower wavelengths, and how absorption is decreasing with increasing wavelength. You find out that relationship. Increasing wavelength, how absorption is changing there, and how absorption is you are getting there, whether it is high or low at lower wavelengths, depending on the wavelengths. Then go for band gap estimation. So 4 points keep in mind while studying the loop. This also I will put. So you have to interpret here from the graph. First is absorption, second is variation of absorption with wavelengths, then how absorption is next it is decreasing or increasing with wavelength. Okay, whether is it proportional or inversely proportional. Next is band gap estimation.
Intensity doesn't matter, right, sir? Intensity.
Intensity, nothing but absorption here, observance versus wavelength. You see, the graph is plotted between observance versus wavelength. So we will give you two Excel sheet, one Excel sheet. So generally you will get two modes, Excel sheet and schedule. Excel sheet is used for object.
What are the working is that intensity at 1.5 and absorption at -1. And the material having some less intensity, 1.4, higher doping or something. That means due to the doping, we can generally understand.
How doping is influencing the absorption. That you must understand. You must understand. Okay, any doubts? You can run this sample again. One more sample or you can take one more. Do one sample.
Yesterday,
In particle size analyzer, what you are getting?
particle size.
Diameter. That is what in nanometer. And it how the you will be getting proportionality and undersize. How much particles are there in which group? Okay, how much percentage of particles are there in that range? That you are getting from PS. Here you are getting the observance, okay, absorption edge and band gap estimation, and how absorption is varying with the wavelengths, different wavelengths, and blue shift and red shift of the graph. And from that you will estimate whether particle size is decreasing or increasing.
Blue shift means particle size is decreasing.
Shift in the graph towards a lower wavelength, that indicates the decrease in size. Red shift increase means increase shift of the graph towards higher wavelength. That indicates increase in size.
So, what if the size increases? That means it is line from
That you are correlate with XRD.
So, if the XRD peak is broader, then it is nanoparticle. If it is very shallow,
That you are going in XRD, but in UV, I'm telling you, in UV analysis, you will see some shift in the graphs. Some graph you will get at higher wavelength, absorption at higher wavelength, some at lower wavelength. Then you have to understand.
If it is having some intensity, then it will be
Some are peaks.
peak.
Yes. You have to identify them.
so what we are analyzing is the band or particle peaks. We are just confirming the materiality.
Yes. You are confirming material, you are confirming the absorption rate. Example, gold. You take gold will show the absorption rate at 300 to 400 plus one is not. Okay. So these will tell you the optical properties of that gold nanoparticle in bulk range or in nano range. You can calculate bulk material also. Nanoparticle, bulk material, different sample analysis. You can do optical analysis.
So in bulk sample means what
For example, you are taking gold in bulk. How it will show some optical property there. When you decrease to nano size, how it is varying. That also you can do.
సూపర్ అన్న సూపర్ నిన్న బాగుంది డ్రాయింగ్ సమాచారం టీ కూడా బాగుంది అందుకే ఉంది అయ్యా
Okay.
అందుకే మళ్ళీ అదే సార్ అట్లనే మాట్లాడుతున్నాను. తమ్మి ఆల్రెడీ వస్తుందంట 2 minutes. ఎక్కడికి వస్తుంది శాంపుల్ నామ్ UV light will be and normal light. The process is first getting the UV light into the particles. When the particle is observed by UV light, then it will send another. When the UV lights are observed by the materials, it takes some UV light and reflects to the unwanted UV. Transmitter. It observes the UV light of some wavelengths and it will transmit from it to the detector, which are not transmitted, that will be detected. Okay.
How much amount?
The observed wavelength will be shown here.
Hey, I know. I know the subject. Yes.
They are roaming with this instrument, so you feel this.
No, I heard only one time.
But you are within here.
Yeah. That
The number of particles observed wavelength.
wait, sir, in the set all this.
I didn't get the
No,
pics.
Exactly only give you the peak. Exactly what? Exactly is the nanoparticle.
That is the UV range which your particles are observed. So your particles are observed at 250. 250. Sir, I consider
Yeah, 2, 3.
it's a good one.
Good one?
Yes.
Mail ID.
Arya 2350 2350 Arya.
Double
644
Arya, who are you?
at SSL.
நான் எங்க சாம்பிள் பண்ணல இன்னொரு சாம்பிள் தான் இல்ல அதுக்கு முன்னாடி இன்னொரு சாம்பிள் கொடுத்தாங்க அததான் இப்படி
Gmail.com
சோனி பண்ணோம்
at SSL.
ஈஸி ரிசர்ச்